Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to new discussion which is DEMs and derivatives part 3. After this we will also have one more part, that is derivatives part 4. As I have been telling you that DEMs are the storehouse of information. By now you must have also realized that so many derivatives can be taken out of analysis of a digital elevation model. And one more similar kind of derivative or products which can be generated, again which is very important, is the topographic roughness. As you go at micro level and start identifying or analyzing micro topographic relief or micro roughness, topographic roughness, you can get few more new types of analysis outputs and applications. So, this basically the topographic roughness is again based on that same concept which we have been discussing, that somewhere you are having a best fit line or a smoothened surface and then you are having the real surface and you are comparing that one. So far what we have been discussing is mainly along a line. Now we can discuss in terms of 3D rather than in 2D. So, this topographic roughness basically, if we want to define, is the relative topographic position, or also in literature you may find topographic position index is a terrain roughness metric and local elevation index. That means this some ratio is there. Now, this topographic roughness, or also we can call as ruggedness, basically is defined differently depending on the which type of calculation we employ. Now, this can be this topographic roughness calculations can be based on either standard deviation of slope or standard deviation of elevation. Generally what we do, we go along this standard deviation of elevation, but depending on requirements. Third way is that slope convexity and then variability of plan convexity, that is the contour curvature, and then again some other measure of topographic texture. So, what we are basically looking are the topographic texture, the variations in elevations in a very local area, very minute or micro terrain features. So, the scale is here important in such analysis. Not only the scale or spatial resolution of a digital elevation model, but at what scale you are going to do the analysis to characterize the terrain or landscape analysis, which at what scale you want, and we will see the example that when we change the scale, the entire output will change. So, this analysis is completely scale dependent analysis. In as you know also in the many cases we start with a smoothed DM like a best fit line in linear or in 2D, or in case of topographic profile we have just discussed, that is smoothed DM produces a more interpretable roughness raster. That means the understanding can be developed very easily while doing this exercise, making a smooth DM and then comparing that DM with the real one, and then finding out where are the roughness which are present at a local level. As we have just discussed that there are several ways to calculate topographic roughness. The topographic position, that is for whether it is a convex area or concave area, for each pixel is identified with respect to its local neighborhood. Also in the previous discussion which we have discussed in terms of using a three-dimensional a 3 by 3 matrix or kernel and finding out the relative position in the what is in the surrounding or neighborhood. And if a neighborhood we finds that there is a depression, that means the center value is less, that means it is a depression. If center value is less compared to the surrounding or high, then it is a a kind of a hill situation or hillock situation. Now this we can only say as index because this is a smooth versus the real one or rough, smooth versus rough. So this index is useful for identifying landscape patterns. We will see some examples. Boundaries that may correspond to rock type sometimes because the surface characteristics are controlled by the rocks, different types of lithologies which are present, different types of soils which are present. So if we find a completely different roughness in two adjacent areas, there must be some region, and one of the possibility that the rocks might be different in those two areas which are showing two different kind of surface roughness or topographic roughness, or also useful for dominant geomorphic features, processes, soil characteristics, vegetation or air drainage in case of desert areas or other things. So classifying this final output raster into high, medium or low based on natural breaks can also be done once this analysis gets completed. And this index, that is topographic position index, is also applicable to bathymetric data. That means not only for the land part which is above mean sea level, but also it can be done for subsurface conditions. Now in short we call as a TPI or topographic position index because in many literature or in software you may find this term TPI in short. So using TPI at different scales and slope, DM can be classified into different categories like a slope position where ridge top, valley bottom and mid slope etc. And whereas a landform category if we define, then steep narrow canyons, gentle valleys, plains, open slopes and mesas etc. So these geomorphic features, because we are going now, if we are classifying into using a landform category, then these would be the categories. If we classify based on the slope position, then we can classify ridge top, valley bottom, mid slope etc. Now there is a special extension which has been developed by a person whose name is Janus, and this I am showing here that extension is available on ArcView GIS, not on the ArcGIS, but anyway that can be used there also. This is very useful tool or extension software tool which can be used to calculate TPI. I will be showing examples very soon. Now the basis of the classification in case of TPI is which is simple, that is the difference between a cell elevation value and the average elevation of the neighborhood around that cell. That is why it is called index. Basically it is calculating a ratio, and the degree to which it is higher or lower plus the slope of the cell can be used to classify cell into slope position. So when you are doing based on the slope position, then this is how the calculation will be done. And of course those slope position, if I want to classify using landform categories, I can still do it. So the same output can be classified two ways. Now the positive value means the cell is higher than the surrounding, while the negative means it is lower. And it is significantly higher. If it is significantly higher than the surrounding neighborhood, then it likely to be near the top of the hill or ridge. And this is very common thing in a like terrain like Himalaya, where suddenly you get something which is very high. So, that might be along near the top of the hill or a ridge. Now, significantly low values suggest that the cell is at near the bottom of a valley. Now, single cell value will not decide all these different mid slope or top or what valley bottom or different kind of landforms. So, few more cells have to be there in the surrounding, and once that is there, then these categories can be decided. So, the TPI values near 0 would mean either a flat or mid slope area, because top of a hill there can also be a flat. So, the cell slope can be used to distinguish the two, which one is, whether it is a flat or mid slope area. Now, here if it is the negative TPI, then that means that either it is valleys or canyon bottoms. If it is positive TPI, that means could be that ridge tops or hilltops. But if TPI value is 0, as we have just mentioned, that is the flat areas or mid slope, then that means flat areas if slope is shallow, the mid slope areas if significant slope is there. So, that means using this index we can assess a terrain from topographic roughness point of view by getting these values. And so, TPI is naturally very scale dependent. This point we have already touched before. Now, let us see the example why it is scale dependent. Three different scales are here, which you can see that it is almost 0 TPI. When TPI is 0 for this area, it is not giving any, because in the surroundings nothing can be checked, because scale is different here, too high resolution. In case of mid resolution, like when it is for the same area, same profile, it is showing the TPI value is more than 0. So, when TPI value is more than, that means the positive, then it is a ridge top or hilltop. So, whether it is really hilltop or ridge top, yes, it is hilltop and ridge top. And if scale, that means the scale is very small scale and very large area is being looked, means spatial resolution of that input digital elevation model is very small or very coarse. In that case, all these changes of the ground or upheavals which are present in the ground or roughness, topographic roughness will not be considered and a large area is taken. That means here the TPI value will become 0. So, what basically this example tells us that even for the same area, if the scale is different or spatial resolution of input digital elevation model is different, the same area will be defined or will be identified completely differently. This would be identified as a ridge top, this would be identified as also a ridge top or maybe some other category, like here which you are seeing the positive or ridge top or hilltop. But when the resolution is very coarse, then this is negative value, that is valley bottom. So, in that point of view, it is really a valley bottom. But if we go at micro level, then it is definitely a hilltop. So, scale, it varies with scale. So, scale is important, or indirectly we can say spatial resolution of input raster grid is important. Now, scale is determined by the neighborhood used in this analysis, and TPI values reflect the difference between the elevation in a particular cell and of course, in the surrounding in the neighborhood. So, it basically also falls in the neighborhood analysis category, and these around cells are there. Now, if instead of schematic, if we take an example of the real one, and the top one is the elevation, that is the digital elevation model shown with the shaded relief model, And as you can see that there are valleys, hilltops and flats are there. So when this the scale is 500 or spatial resolution of digital elevation model is 500, this is how this TPI has been decided. The neighborhood TPI minus 3 to 350 to plus 350. So hardly you are seeing few hilltops which have been identified when this is the scenario. But when spatial resolution is 2000 meter, then I am seeing many hilltops areas very easily, and large valley bottoms are also there, and TPI values are also very large. What we conclude here, that coarser the spatial resolution, higher the TPI value can be, or large variation between minus and max plus values can be, like here minus 650 to plus 650. Whereas if resolution is very fine or high resolution, like in this example relatively 500 is high resolution, and in that case TPI value relatively will have less range, minus 350 to plus 350, and identification will also. So this is that is why it is said that this TPI is completely scale dependent. Now based on this we can also perform the slope classification based on slope position, that TPI values can easily be classified into slope position classes based on how they are. For example, if a small neighborhood slope, that means the high spatial resolution, then like this area is being identified as ridge, whereas in case of coarse resolution this area is being identified as a valley. Similarly here in case here lower slope, and whereas it is being identified as ridge, it is flat, so it is identified as a ridge, it is a valley, it is a middle slope. So only the middle slope valleys are identifying correctly or the same way in both the scales, but otherwise things are being identified differently. So depending on your input resolution of your digital elevation model, this analysis can be done. Now here again that same example, but based on the slope classifications, that here your input digital elevation model, this is the slope map on the top right, and then slope position again 500 meter spatial resolution, 2000 meter spatial resolution, and here see the valley part in the right hand image, that is 2000 meter, is very large, and same with the ridge part. Compared to 500 meter spatial resolution, both valley and ridge areas are relatively very small. Terrain wise is same, except the resolution has changed and your identification of different features based on slope classification will also change. Now you can classify based on the landform categories. We have also seen examples where you require two TPI grids at different scales, say for example 500 and 2000. Combining TPI values from different scales suggest various landform types, like here we can combine and can come up like this one and this one. So both are SN and LN, means high resolution and low resolution are here, and then you get very clear idea about what is happening. So by combining these two spatial resolutions, if possible, you can classify based on the landform categories your, and of course the TPI, that is large and small neighborhood TPI. So the classification can be done likewise also. High TPI value in a small neighborhood combined with low TPI value in a large neighborhood would classify as a local ridge or hill at a larger valley areas. Whereas a reverse to this, a low small neighborhood TPI plus a high large neighborhood TPI can be classified, would be classified as an upland drainage or depression. So all those in that summary here, that these are the values which are shown the TPI on the both x and y scale, and as you move all in these 8 directions, you get different classifications. So, like slope, this sharp ridges and high peaks opposite to this is deeply incised canyons or valleys. Similarly, mid slope ridges here upland drainage or depressions. So, likewise based on the TPI, here is the negative small neighborhood TPI, here is the positive small neighborhood TPI, whereas here you are having negative large neighborhood TPI, here you are having small or positive large neighborhood TPI. So, based on this, the classification can be performed quite easily by combining two also. Example here, 500 spatial resolution TPI and again 2000 meter spatial resolution TPI, two different classifications. These maps we have already seen. Now, when we classify based on slope or landform categories, these are the categories which we can do it. So, a simple digital elevation model, when it is subjected to this topographic profile in position index calculations, and any of these two basic methods can be employed, either slope classification or landform classification or categories classification, we can create very useful products like here. So, that means employing a digital elevation model and a TPI, a geomorphic study or automatic detection of landforms can also be done employing these two things along with the digital elevation model on a GIS platform. Now, there is some variation to TPI index, that is the terrain roughness index. This TRI provides a rapid objective measure of terrain heterogeneity. So, everything is related with roughness, and this roughness is the degree of irregularity of the surface. Basically these are the micro terrain features which are useful in many analysis from soil erosion point of view or from sediment transport point of view or from mineral exploration point of view. So, this is calculated by the largest inter-cell difference of a center pixel or center cell with the surrounding cells. And this determination of roughness plays a role in the analysis of terrain elevation data, useful for calculation of river morphology, in climatology, physical geography in general, and in many civil engineering projects as well. Now, algorithms which is employed here to calculate this TRI is basically the sum change in elevation between a grid cell and its 8 neighboring cells. So, again this 3 by 3 kernel will be used, and therefore, an increased TRI shows increased local relief heterogeneity. And this if we compare TRI and TPI, as you know, the topographic roughness index is basically the mean of the absolute differences between the value of the cell and the value of 8 neighbors, its 8 neighbor. And whereas in TPI, the difference between the value of a cell and the mean value of its 8 surrounding cells. So, there is a calculation difference, that one is basically with the surrounding 8 cells, and here is the mean value of 8 surrounded cells. And whereas here the value and this is the absolute difference between the value of the cell, whereas is the value of the difference between the value of the cell and the mean value. So, why this is also the mean of the absolute difference. So, either one is taking the mean of the center value, or in one is taking mean of the difference value, and then these two indices can be used, can be derived implying a digital elevation model, which can be very useful for identifying steep areas, steep roughness or rugged areas, and you can give some quantities. instead of qualitative analysis. Now, this topographic position index can also provide some valuable information about geomorphology of the region which we have just discussed. And this roughness, that is the topographic roughness index TRI, is basically the difference between the maximum and minimum value of the cell and its surrounding cells. Example here, that this is a geological map which is shown here. Different geologies are lithologies are present here, like marine deposits, ophiolitic formations, granite, granotirides, etc. Now, when it is subjected to this calculation, that is the TRI, this is what you get. So, based on then slopes, this is how the terrain is classified. When we see the valley depth in meters, this is how this is there. Then when we see the TRI, this is the situation, and TPI is like this. Of course, TPI of course will depend on the scale or resolution of your input. So, here is only one. So, DM has been employed to calculate slope, valley depth, TRI and TPI. All these parameters or derivatives can be derived employing a digital elevation model, and lot of useful information can be extracted for various applications. Again, that TRI and TPI values are there. The valley depth refers to this output, is referred to the vertical distance to the channel network base. This calculation can be also useful for various applications. Here I have taken example from this publication, is that for overall India they have derived TPI as well as TRI, and for different scenarios these things have also been presented here. So, that regional scale over a target area in South Asia, different scientific observations and auxiliary data were depicted. TPI, TRI, BRM and so many other parameters. What is the input? A coarse resolution digital elevation model to cover a regional or continental scale analysis. So, this brings to end of this discussion about TPI, TRI and their comparison and various other related also indexes. Now, the purpose here is to exploit digital elevation model to its maximum. Sometimes we have to employ for the same reason two different spatial resolution digital elevation models to derive some important information like TPI. So, with this I end. Thank you very much.